And this week we're going to hear from Isaac, and he's going to be talking about Approximate Bayesian Computation.
Yes, ABC. Very simple, just like ABC. Prepare for a bunch of terrible, terrible jokes.
Excellent.
Yeah, very terrible jokes. So this is a very, very basic introduction to ABC. And so basically to start off with, I wasn't sure if maybe some people here haven't really had a lot of exposure to Bayesian statistics, so I just wanted to mention a few things first off. That basically in Bayesian statistics, what you're doing is you're treating unknown parameters as random variables. Then you're going to use the distribution of those random variables to describe your uncertainty about them. You then do the same sort of collect data, improve your knowledge about the world, and that's loosely, you're getting data, reducing the variance of those parameter distributions until they concentrate on the truth. So approximate Bayesian computation is a technique for applying Bayes' rule in order to be able to compute these updates without any assumptions. Later on, throughout this talk, we'll do a couple of simple examples. I will also send out the source code for all of the examples so you can take a look at them. They're very, very simple, so you should follow. And also at the very end, I'll apply ABC to locate special nuclear material, which is a problem that I'm working on in my research. So you can see an actual application of this. So I'm going to be very audacious and introduce Bayesian inference more rigorously in 1 minute. So with Bayesian inference, basically you start off, you have some sort of model, statistical model that describes how your data is generated if you knew what the parameters were. You introduce some sort of prior distribution for your parameters. So that's what your belief is before you've collected any data. You then are interested in a posterior parameter density, which is then your belief after you've collected data. So that's your parameter conditioned on the data that you observe. And the way that you calculate the posterior is by using a variant of Bayes' formula, where you take your model, multiply it by a prior, incorporate the data that you've collected, and then normalize it so that it is in fact a true PDF. So in Bayesian statistics, basically the inference that you do, the information that you're gaining about the real world, basically it's all coming through this posterior distribution. So you can take this posterior distribution and do whatever game you want to play with it. You can ask it, well, what's its mean, what's its median? You can look at critical intervals. You can do anything. But basically, once you have that distribution, then you're golden. So essentially, computing the posterior is the name of the Bayesian game. So as a basic example of how all this goes together, let's design a highway. I have no idea how to design a highway, but sure, let's do it. So should this highway be 2, 3, or 4 lanes to ensure that you have fluid circulation? Well, you got to figure out how much traffic is going through it, so let's get some data. So what I'm going to do is I'm going to sit next to an off-ramp, look at how many cars pass by. So the data that I'm going to collect is going to be a Poisson random variable, number of cars that pass by in a single minute, with theta being the rate parameter. So that's the rate of cars passing by per minute. I have no idea what that is, so I'm going to just, for expediency's sake, I'll allow theta to be uniform 0, 1. So I'm basically willing to entertain the possibility of this no cars passing through this stretch of road in a minute, all the way up to 100 on average. So that's relatively wide. So I then go and collect some data. So I've collected 3 observations. I'm very, very rigorous. I like to have lots of data. So taking that, we then are going to plug that data into our model, get our likelihood, combine that with our prior, which is right here because it's a uniform, so we have 1/100 indicator function, and we have our Poisson likelihood right here. So our posterior here is at least proportional to this. So this is only that top of the numerator that we had on the previous slide, because we then need to normalize this. That's where it gets a little bit hairy. But the key is basically if you ignore this, ignore all of this, and you look at what's here, you think back to 521, what's it now,
701.
701, all right. Think about 701, you identify what the kernel is, and then you integrate it because you've already seen that's clearly some type of gamma. So you identify it as a gamma 85 1/3. Well, almost. I was being a little bit lazy here, just because technically you have some sort of incomplete gamma function running around in there, but it's pretty close to the same thing. This is something you should realize is always people, forget all the details when they're writing stuff out and say, it's good enough. So, just be careful. But this is a lot easier to deal with than incomplete gamma functions. So if you were to actually plot what happens once we've collected data, our prior is this flat line here between 0 and 100, but then when we've collected some data, we've concentrated around the sample mean, close to 28. Basically, we could have some relatively low rates and we just saw ones that were higher, or we could have higher rate, we saw ones that were lower. All of these are kind of really plausible cases that the true parameter could be in. The one thing you should note is that the posterior mean, that's a little bit higher than the sample mean. And that's partially because we incorporated prior information where we said that our car rate could actually be as high as 100. So because we were willing to entertain such possibilities, that's going to slightly skew our posterior mean slightly. So, all right. So, as we've shown here, basically, once you can compute that posterior, you're good. So, we have to tackle this guy right here. So, first off, you can do it analytically, which is what I kind of did before. No, we're not doing that. That's just terrible. Well, no, it's interesting, but it's fun. It's a fun thing to do on the weekend, but it's going to take forever. So, and it only happens in special cases. Like I did like a uniform at Poisson, and all of a sudden you're already working with the incomplete thing again function. Okay. So, what you could do is you have to calculate that normalizing constant, so that's just integration. Well, you can do it numerically. So get out your trapezoid rule from Calc 2, I think. Do something like that. That might be boring, but also it's going to be problematic once you get into higher dimensions. You could also do this sort of approximately using Monte Carlo integration or importance sampling. So those are two possibilities. The big heavy workhorse of Bayesian statistics is Markov chain Monte Carlo methods. So these are really, really nice because basically they skirt the whole issue of calculating this normalizing constant by instead creating a Markov chain, which you sort of you're really stochastically sampling from the posterior distribution by setting everything up right, such that this Markov chain converges to that posterior distribution. It sounds really complicated, it's not too bad in practice, works very well, and this also includes Gibbs sampling if you ever come across that. You can then get into fancier things like sequential Monte Carlo, SMC, particle filters, and oh man, I'm throwing all these buzzwords out at you guys. These start getting a little bit hairy as well, but they're interesting. But all of this stuff, this is way too complicated for me. I need something simpler. So we're going to talk about accept reject sampling. So this is a basic idea from chapter 5 in Kessellenberger. So basically everything comes back to 521, everything I learned from that class. So basically if you wanted to say sample from a uniform distribution over this triangle here, but you can't do that because you don't have a thing in R that says sample from a triangular uniform distribution in 2 dimensions, well you can sample from a rectangular one, throwing 2 uniforms together. Well basically what you could do is just sample from what you know and throw away everything that is inconsistent with what you want. So sample on the square, throw everything away except for what's in the triangle. So it's a very simple idea, but that's what kind of underlays a lot of random number generation. So if I want to do this with calculating that posterior distribution, what I can do is I sort of already know what my prior is. As long as I chose a relatively nice one, I can sample from it. So I can draw a theta then, because I know what my model is, I can then plug that parameter into it and draw from that model. So I can simulate data, and then I can just look to see whether or not that data that I simulated matched what I actually observed. So if it matches what I actually observed, I can say I accept that theta that I drew, because that basically is it's a parameter which generated data that's very similar to what I saw. So if it actually did produce that, it's still a plausible theta. All right, let's keep that. Let's look at it later. If it doesn't produce it, reject it, because it doesn't generate what the data was. So it's not explaining that data. We don't want it anymore. Okay? Well, if you do this, we could then take this algorithm, repeat this until we've obtained a certain number of posterior samples. We can then basically, one second, need some more. These accepted thetas are being sampled exactly from the posterior distribution. Because literally these are the parameters which satisfy the condition that the simulated, what we're exactly seeing what we saw in the real world. The only problem though is that this is computationally infeasible, because this equality here, that's going to be tricky, because you're doing the simulation, you're trying to hit a target that may be really difficult to hit. Because imagine if this model here is continuous, every time you sample from that, that could be some real value, probability 0, you're ever going to actually see the same data that you actually saw in the real world. So you would never accept it. So even though in theory this could work, no, not good enough. So let's introduce approximate Bayesian computing. What we're doing is we're just going to relax that equality a little bit. So instead of saying that we need to match the data we saw, let's just say we need to get close to that data. Okay? For a sufficient definition of closeness. So we're going to follow the same pattern, draw a theta, draw some data, then we're going to measure the distance between the observed data and the simulated data, and just see whether or not they are sufficiently close for some metric d. So if in distance they're within epsilon of each other, then we're going to say that's a pretty good approximation. Otherwise, we throw it out. Do the same exact trick. We're going to repeat until we get n posterior draws. The tricky part, though, is that basically instead of sampling from the true posterior, we're sampling from this guy here, which is that we're sampling from theta conditioned on this distance being less than epsilon. So it's close, but it's not exactly the same thing. All right, okay. So obviously the big question that you guys all have, why am I doing this? Or why would you want to do this, other than it being the greatest thing in the world? Not really, but the key here is that there's a subtle difference between what the model is that you're working with and the likelihood. So in the Bayesian statistics, you're technically not really using the model, you're using the likelihood. And those things can be, those have a slight tricky thing about them. So basically your model, that describes, what if scenarios. They're saying that okay, if I have a particular theta, I can then figure out what the probability is of getting a particular set of data. So it's very forward oriented. So you're making sort of predictions in a way. The likelihood, on the other hand, that's sort of explaining what's happening, or explain what has happened. So it's trying to do more of a backwards direction. And it's very easy to go forward, but it's more difficult to go backwards. So for example, you don't study for the basic exam, how are you guys going to do? Just fantastic. Oh, okay. Probably you're not going to do very well. So you kind of given this, what's going to happen? But instead, if you just you did poorly on the basic exam and then you have to explain why. That's trickier. Well, did you study, did you sleep, did something happen? Like, that's a much more complicated question, much more difficult to answer. And so, basically, all right, oftentimes it's much easier to create models than it is to compute likelihoods. So, for example, if you're looking in like population genetics, astronomy, system biology, all of these fields in science, they have a lot of models that you can then generate. You know, you can have dynamical systems, you can create simulations of, well, in these particular sets of parameters, this is what you expect to see. Imagine like, you know, huge galaxy simulation in which you have stars rotating around galactic center or something like that. You can do that. It's very different though to take some observations and then infer back what those parameters are. So basically, the nifty thing about this approximate Bayesian computation is basically you don't need to compute a likelihood. All you need to do is be able to do forward simulations. So I just need to draw a parameter, forward simulate, then see if it matches what I observed. You don't have to work backwards. So does this even work? Well, let's go with the simplest example that we could possibly do, work with some normally distributed data. So here we have a model. I'm going to sample normal with an unknown mean with a variance of 1. We have a prior here. Our prior for mu, we don't really know what it is. It's going to be centered at 0 with a variance of 100, relatively wide. I observed 2 pieces of data. Again, this is big data here. 3 and 4. Because this is, we're dealing with a normal model, normal prior, the posterior you can calculate. It's not too bad, especially under these conditions. But the posterior here, it's a normal with a mean of 3.8 and a variance of 0.5. Those are rounded a little bit, but that gives us something to compare to. So for the ABC approach, what we're going to do is we're going to do 100,000 draws from our prior. So 100,000 from this guy here. We're then going to simulate, we're going to generate 2 observations from that and compare them to what we observed. The epsilon that we're going to cut off using the Euclidean norm is 0.6. Technically, I did this as being like implicitly defined because what I'm doing is actually accepting the smallest 1,000 distances. That's a very common technique that they use. It's not necessarily the best thing in the world, but it's a simple kind of thing. You don't have to sit there changing epsilon, but you still kind of, that's not perfect. But let's see what we get. So when you look at the histogram of these Euclidean distances between the simulated data and our observed data, we get this guy. So it's something that's nicely right skewed. You can see that some of the time we end up with like really, really different data from our simulation. Most of the time it's relatively close. This is still like a bin of, this is from 0 to 5 distance. But really what we're going to do is we're going to focus in on the really small ones. So when you then plot here, this is our analytically obtained posterior distribution. And right here, we have a KDE estimate of the ABC posterior. So this is the 1,000 draws that we have. A nice smooth curve there. It's reasonable. You have something that, you know, you have sort of the lining up the modes. There's a little bit of a difference though. Sort of the peak isn't as high here, and the tails on the ABC distribution are a little bit heavier. Which kind of actually makes sense because you're kind of being a little bit loose with everything here. So the ABC, you would expect it to be a little bit more liberal with what it would say are acceptable points. Okay, so, but we can do a little bit better than this. So we can improve the performance. Basically, well, one is you could make M larger and epsilon smaller. That's my contribution. Unfortunately, that's already been published, so I can't have my PhD. So the key is, though, is to work smarter, not harder. Because if you do these two, you're going to have to do way more computation, more simulation. So instead, the trick is the other thing that you do in statistics, you reduce the dimension as much as you can. So basically, this now 522, which is now 702, coming back, is this kind of coming out when I was doing all this stuff. It's like, oh, it's like all just, stuff you learned in those two classes and math stat. But you look at sufficient statistics. So you say, like, you look at some statistic that's based on a sample that you observe. Is it sufficient? That's when the conditional distribution of your data, given that statistic, is free of your parameter. So that means that, another way of saying that using the factorization theorem is that your joint model, joint density, factors into a piece that depends on the parameter and the sufficient statistic, and then you have some random stuff that doesn't depend on the parameter at all. Thank you, Casella and Berger. So the key idea here is that sufficient statistics, they summarize all the information about the parameter that's contained in the sample. So the simple idea is you can take a sample of 100, but you can easily summarize it by a mean, which is only one dimensional, assuming it's normal, and that's the only, you know what the variance is, and all details. Yeah, so let's apply this idea to ABC. So back to that same normal example. So before, we were taking and we were simulating two observations, an x1 and x2, both with normal mu1. Instead now, let's try to match the sample mean. So that sample mean, the sampling distribution, that's going to be mu with a variance of 1 over square root 2. And then we draw 100,000 prior draws, do the same exact thing, same amount of computational expenditure, except 1,000 small differences. We look at what we get. So here, our sufficient statistic based one, this is the small dotted line, that improves quite substantially. So we're really matching the curve there very nicely, both in the tails and also at the peak. So part of what's going on here is like before, if you have like a really high dimension, like if you're using the raw data itself, there's a lot of different orientations that data can have. So in 2 dimensions, just because your first simulated observation isn't very close to your first true data observation, it may be that, well, when you consider the two as a pair, they're actually much closer if you flip them or doing something similar like that. So by switching to sufficiency, you're removing all of that excess baggage that you don't need to worry about. So basically, sufficiency is giving you a lot more bang for your computational dollar, which is great. And so then basically, the whole procedure of applying ABC is to iteratively apply sort of more and more refinements to the algorithm this way. So how can you improve it incrementally? So wait 1 second. So you guys, clearly I know that you guys have this question in your mind. Is that, well, the whole reason I told you about doing ABC was you can't compute likelihoods. Well, I just used sufficient statistics to make this better. Sufficient statistics involve factoring a likelihood. That seems a little bit of a cheat, and that is. Because really, what are you going to do instead? Use some magic. This is where basically it's like, well, you're already doing an approximate, but what's the worst that could happen if you approximate some more? So what people end up doing is figuring out ways of approximating sufficient statistics. So basically you can throw in and use things like PCA or maximum entropy, and basically what you're trying to do is you find informative summaries of the data. So you're trying to maybe take linear combinations of the data. That way you can then figure out which are the most informative linear combinations, and then use those as the statistics that you're going to match in the ABC algorithm. So that's obviously not really truly sufficient, so you're going to be breaking part of the algorithm that way, but it still gives you some, it's better than using the raw data. It's at least you're trying something. So, all right. Now to some little bit of theory, just a little bit, not too much. Does this actually really work at all? And so you can actually prove a theorem where, say, if you've observed X star as the data that you've actually observed, and you have some sort of density for your sufficient statistic, and also just remember this generalizes to, you can use all of the data because the whole sample is a sufficient statistic for the parameter in that case. But basically in this first part here, this is the nice part, is that as long as this density is continuous and also uniformly bounded within the neighborhood of the observed sufficient statistic, as long as you have that, so you have a relatively nice density, nothing too pathological, and you allow this epsilon to go to 0, and then in that case you actually are sampling from the true posterior. Basically what you're doing is you're taking my algorithm 2 and then pushing it towards algorithm 1. So you do actually get the true posterior out of this. This is a relatively rigorous, like not very rigorous, but you can make it more rigorous. The negative thing though is that that's going to take more computation in order to achieve that. So the average number of samples that are required to get one accepted parameter from this posterior distribution is on the order of epsilon to the negative q. So epsilon is whatever the epsilon is that you're using here. So if you make that smaller, this is going to go up. Q is the dimension of your sufficient statistic. So if you all of a sudden start dealing with a larger sufficient statistic in dimension, that's going to increase your computational cost as well. So both of those make sense. That just is kind of unfortunate because you'd really like to, I don't know, have that order 1 or something like that and be an excellent. So, and then there's going to be some fudge up to the particulars of the model that you're working with. Yeah. All right. So, are there any questions so far?
Isaac, can I kind of ask just a general question? So it sounds like you can use this where you have trouble, you've got a fairly good, say, mathematical or physical model, but maybe not a very good statistical model. Is that a fair thing when you're talking about not being able to build a likelihood?
Yes.
Okay.
So, let me maybe go back to, yeah, right here, is that, so typically, and this is an overgeneralization, is that if you have, say, like a any type of like epidemiological model or some sort of, you know, something that's like growing exponentially, or you have some sort of system of differential equations that defines a model, then you can run that model with some parameters. You could end up having some stochasticity in it or whatever. But when it comes to fitting the likelihood, oftentimes people will assume that you have normally distributed errors.
Exactly.
Which, if you assume that you have a normal distribution on your errors, then all of a sudden this whole issue of whether or not the likelihood is well defined or not goes away.
Right.
Because you know what it is.
But it's often really a bad assumption.
Yes. So that could be a bad assumption. Where this can fall into is well, maybe instead of having tacking on that error at the end,
right,
but as an assumption, perhaps you can incorporate that stochasticity into the simulation or to the model itself.
Yeah.
And then as you're running it through, then you can allow the error distribution to just sort of manifest itself however it needs to be.
So that's what I thought. And so where this question is going is one of the huge problems we have, as everybody knows, is model discrepancy. So you've got this model, you think it's pretty good, but it's off. So then you assume your normally distributed errors, but they're wrong. And you've got this model discrepancy term sitting in there. And there's all this kind of general approaches to try to back that out, but it's really hard. Does this give you a shot at trying to deal with the model discrepancy by building the stochasticity into the simulation model itself? You see what I'm asking?
I'm not 100% sure.
Okay, no, that's,
yeah, no,
this is a really kind of deep, open question. And
yeah, I mean, I guess partially it depends on how well you can you can validate that simulation in some. Is it
Right.
really is it really actually producing realistic output?
They'll often be realistic, but the easiest case is you've got realistic, but then you've got this bias sitting there.
Yeah.
And so you say, okay, as soon as I've got a bias, I obviously have just blown my normally distributed observation noise. And one of the things that people have done on that is to say, well, let's try and embed these uncertainties into the model itself, because additive just is too simple.
Mm-hmm.
And the way you describe that is sort of philosophically similar to embedding some of this uncertainty into the model itself.
Mm-hmm.
So let's keep talking about that one offline. That one was sort of a massive, big question.
Yeah, definitely. All right, so, yep, back to magic. All right, so, so just as a flavor of like what I'm working on, so this is a problem that I'm working with Dr. Smith on, is looking at radiation sensor networks. And so like this was sort of the motivation for even looking into this ABC stuff, other than it being really interesting in its own right. So this is work that's done through CNEC, the Consortium for Nuclear Non-Proliferation Enhancing Capability. It's quite a mouthful. But the goal that we're trying to do is we're trying to identify a radiation source within an urban environment. So it's a relatively difficult problem. So here we have a little visualization. Here we got a city block in Washington, D.C., bunch of buildings, bunch of sensors set up around the block, and you have a source that's somewhere within there. And so what we want to do is take measurements from the source, and measurements of the gamma rays coming off the source at the different sensor locations. We model each one of the sensors as a Poisson random variable with a mean that depends on the orientation between the source and the location of the sensor. And so that's what this thing is here. So this thing's looks a little scary, but to explain it more or less is that radiation, it's like any other type of like light or any type of like propagation of energy, is that it follows an inverse squared relationship. So here we have distance between the sensor and the source, inverse squared. So the further you are away from it, the weaker the signal will be. Over here you have a background radiation term that you can incorporate some information about naturally occurring radiation. And then the important term right here is this exponential sum, where all of these terms up here, what they're doing is they're describing what's happening to this radiation as it's passing through buildings. So as, find a good one here. So let's say if we take this sensor here, basically the radiation that's coming off of the source, it's going to be decaying somewhat differently while passing through this building, or being attenuated is the more technical term, differently than if it was passing through air, because it's passing through walls and concrete and things like that. It will then go through some more air and then through another building. And so basically what we're going to do is we're going to sum up the effect of each building and also the distance that is traveling through that building. We're going to do that for every single source. And so this is what makes the whole problem of doing the radiation localization within an urban environment difficult, is because you're dealing with a very heterogeneous landscape, where not only are you possibly dealing with like small amounts of data, because you can't have an infinite number of sensors everywhere, but the likelihood also is not going to be smooth, because basically the observations that you're going to get are going to be radically different depending on where the sort of the geometry is between the source and the sensor. So if you were to take an observation here, it's going to get clipped by that little piece of building there. That building's made out of concrete. That could change quite radically than if you took a couple of steps this way, and all of a sudden you have a much clearer line of sight. So there's a lot of interesting physics in there that I don't completely understand. So the important thing though is that if you're then going to apply this to a non-proliferation kind of thing, you want to keep radiation or radioactive substances out of the hands of bad guys, you need to be able to do this a little bit more in real time. So just because we can calculate all of this stuff theoretically, given enough time, we need to be able to do this faster. So that's kind of where I've gotten into this ABC, is being able to try to calculate posterior distributions in this kind of really crazy setting where typical methods are going to fail. So here we got, hopefully you guys can sort of see this. The color is kind of crazy, but so here I'm putting a source here. This is the cyan dot right here. So that's some radiation source. I then have 3 sensors at the green dots here, so they're just kind of not uniform, but just kind of evenly spaced out within the block. We take 5 observations, so 5 Poisson random variables from each of these sensor locations. As you can see, none of them are really super close to the true source, so they're all going to be relatively kind of like middle value, not crazy high, not crazy low. Okay. And it's really only 15 total observations, so relatively small amount of data. So I'm going to take these sensor means as our sufficient statistics, so you just take the average of each one of those, because those are all going to have different rates. So we need to incorporate those. And I've taken 15,000 forward samples using uniform priors. So I set up, basically I say, before I know where the source is, I would be willing to entertain from 0 to 250 meters on this side, 0 to 175 meters on that side. And then also I have another parameter that describes the intensity of the source, because depending on the size of the source and what it is and all that sort of stuff, it could be anything within a range, put a uniform on that. So I sample from that 3-dimensional uniform distribution, and I accept 1,000 best parameters and see what happens. So basically what we have here is we have this is a heat map, this is a kernel density estimate of the posterior distribution over the x and the y parameters of the source location. So I'm not including anything about the source intensity, but basically based on what we've seen from these 3 locations, essentially we have 2 modes, one right here around the actual true source, and then we have a little bit of fuzzy hazing out here. And so what we're seeing is that while these are all locations where it's sort of plausible that the source could be, with 2 main peaks. And because I didn't plot the intensity here, you would also see that there's separation between these 2, not just in the physical space, but also in sort of the intensity parameter. Because given these observations, you can either explain them using a lower intensity source here, that's sort of closer to the middle of all of them, or a higher intensity source that's further away. So it's one of the 2. So when we then would go and take this, we could take this posterior distribution, because as I said in the beginning, once we have the posterior, everything, we're good to go, is that we can then use this to guide where we're going to take observations next, to be able to identify the true location. So we would definitely want to take something over here, and when we do that, we're going to find that the intensity really isn't very high here, not as high as we would anticipate. It would be high here, we would find the source. So that's what I'm working on, is figuring out ways of how do you guide that search strategy based on taking these posterior distributions, calculating different statistics, doing some optimization, to be able to inform the placement of sort of where should you then take sensor readings next in order to identify the location. So I put here the runtime. So it took about 30 minutes on a single core computer, and basically all of that time is calculating these forward simulations over and over and over again. And so this is actually about like half the time that it would take to use a more traditional MCMC approach to this problem, because this is, again, one where we know what all the priors in the model are. They're all relatively nicely behaved, but if we run the ABC, we can get the runtime down quite substantially, and also it allows us to look at the entire space where we still have some small probability in these other regions as well. Whereas like traditional MCMC approaches kind of get bogged down in this multimodal sort of situation. And also I mentioned that it's a single core because you're just doing these forward simulations, you can do them in parallel. So You take an 8-core computer, you can cut that by a factor of 8. So you can actually get this down to the point where it is in real time, given pretty reasonable computational resources. So some caveats though, as we're wrapping up here, is that one thing is, I don't want you guys going out here and using ABC irresponsibly, so is that you need to be very cautious. Is that basically the only, like the real reason why you would be using this method over an MCMC is that you're working in a really complicated situation. And doing really easy things in a complicated situation is a recipe for disaster. So what you want to do is, you're probably not going to have any analytical or numerical results to be able to verify your algorithm. So you're going to want to be very, very careful about interpreting the results. This ABC is also, can be computationally very expensive, but basically every Bayesian method is more or less computationally expensive, so that's not necessarily a bad thing, but just realize that. You're doing a lot of work for a very little amount. It's like that you have to do a lot of forward simulation to get a little sample, but that sample can be pretty good. One important thing, and so I didn't dwell on this at all, is that when you're dealing with these sufficient statistics, those aren't necessarily on the same scale. So you could have one sufficient statistic that varies over a wider range than another one, and you'd want to end up scaling those such that when you calculate your maybe Euclidean distance, you don't want to have one of these statistics dominating the decision of accepting or rejecting. So that's an important little tidbit there. And the last is, again, being cautious. Don't be happy with the first thing that comes out of this thing. Because, well, you should run it many, many different times. Use different epsilons. Calculate the ABC multiple times using different random seeds and compare the results. Because, again, you don't have an analytical solution to compare to see if you're doing it right. You have to basically look at whether or not there's any sensitivity to these tuning parameters. So if you change epsilon, or if you change like the number of samples you take or anything like that, or if you change the random seed, does the posterior that you end up getting out of it, does it change a lot? So if it changes a lot with these parameters, that's a sign that you need to be very, very careful in actually utilizing that posterior distribution for calculations. But sort of the positive is that ABC is a nice, quick, it's a little bit dirty way of estimating a posterior. It works in cases where you cannot or are unwilling to compute a likelihood. So it's great for the lazy people like me. There are problems. These types of problems, as me and Dr. Smith were mentioning, is like that these happen a lot in science where you are able to create models, but you can't necessarily compute a likelihood that isn't making really huge assumptions. And although it's computationally expensive, it is very easily parallelizable. So that's a, if you got more than one computer, you can double your speed. And a couple of references here. So I'll give Dr. Post these slides so you guys can get them. This is a very entertaining blog post here, if you're interested in Bayesian statistics and socks, in which a guy, he computes the, sort of tries to estimate the number of pairs of socks that are in a washing machine based on the number of pairs of socks, or unique individual like right socks that he pulls out. It's very interesting. But this is an example where in the comments then people are complaining, well, you could compute a likelihood. It's like, well, yes, in theory you could, but when you actually look at the details, it's some sort of monstrous like multi like hypergeometric distribution, and it's just, that would take a long time to figure out what exactly all the details are. These are two good sources, and there's an R package, nicely named ABC. So ABC is very simple, but they do incorporate sort of like data structures that make it a little bit easier to handle these large forward simulations, so that you can like go back, change the epsilon very easily, things like that, and then they have some very basic diagnostic tools and stuff. So it's a nice little package, but it doesn't really actually implement the guts of it, which is really coming up with that forward simulation, which is really the most difficult part. Okay. So that's everything I got. Wow, exactly at 250. Unless this is, well, it's nice.
That was to within a second. That was good.
So you're going to make the source code for the simulation you ran there available as
Yeah,
well?
for everything except for my research stuff, because that I can't do tech support on that. But yeah, for all of these things here, yeah, it's very, very simple. So it takes 5 minutes to code out. Obviously, if you do more complicated stuff, it's going to take longer. But that way you can play around with it.
Can you go back to your research one? So how do you teach the computer like the geometry of the landscape? I guess like where the buildings actually are.
Okay, so like what there is on the back end, and this is where the computation time really increases, is that there's a shapefile that describes the outlines of all the buildings, and then there's also a file that describes the cross-section, which are the sigmas there, I believe, right? No. Which that's describing how much the radiation is attenuated by that building's like composition.
Sure.
And so on the back end, you end up just calculating using like a ray tracing algorithm. You figure out the straight line between those, and then you add up sort of the total distances along the line that are intersected by buildings, adding in their cross section. Interesting fact while I'm mentioning this is that the cross sections, those are describing like how the radiation interacts with materials. So every material has a different cross section. The units that they use to describe that are in barns.
Yeah.
Right, Rob?
Yeah. Yeah.
As in whether or not you could hit a barn, the side of a barn, which is sort of, I just find it hilarious.
A lot of nuclear engineers have really interesting senses of humor. And Barnes is one of them.
Yeah. Any other questions?
So you sort of addressed this in your be cautious slide, but in terms of just like the basic example problem where you take 1,000, choose the 1,000 like lowest points, how much does that distribution change if you took 2,000?
Ooh, yeah. That could end up changing quite significantly, and that would then go through all this stuff. That would also be impacted a lot with this thing, because if you were using changing what the epsilon was, and you didn't have that really small, then basically you could end up accepting sort of slightly skewed results. And so yeah, that is exactly the kind of thing you would need to look for. But yeah, so.
So you said, try it with different seeds and different tuning parameters and see how different the posteriors are. How do you measure the difference in the posteriors? Is there a common way for doing that, or you just look at it and say, this looks odd?
That would be the first test, yes. I mean, like you could do, like, depending on how many parameters you had, do QQ plot sort of stuff.
Energy statistics might be one thing it seems.
I don't really know that as well.
Non-parametric comparison of
Yeah. Yeah, so you could do any type of non-parametric comparison. But yeah, most likely it would just be a first visual test. Is this one particular simulation up in this corner and this one down in that corner? Something you don't really need a statistical test to tell you that there's something wrong. But yeah.
All right, thank you guys.